All right, let's start with that problem on the board. We have dy dx equal to 9 times y over x. And x naught is 4. And sorry, y naught is 4. X naught is 1. Or in other words, y of 0, sorry, y of 1 is equal to 4. Okay, so when you see a differential equation, the question you should ask yourself is it separable or is it first order linear differential equation? It doesn't look first order because I don't see the usual y prime. I mean, there's y prime, but I don't see like y prime plus y times the function of x equal to function of x. Although technically you could make this one first order linear. If you really wanted to, this is inside here, you could write this as y prime minus, or I'm gonna say plus negative 9 over x times y equal to 0. You shouldn't do it this way, but sometimes a differential equation is both separable and can be done first order linear. So just as an FYI, sometimes you can do it both ways. But let's do this one the sensible way. It usually makes sense to do it separable if we can. I'm going to put my y's on the left. I'm going to have a 1 over y times dy equal to a 9 times 1 over x. And you could put the 9 on the other side, either times 9 over here, divided by 9 over here. If it's up to me, I usually try to put more stuff on the independent variable side. Sometimes put more things on the x side, less things on the y side. Because we're going to try and solve for y. So it's better to have less things attached to y to start off with. Then we're going to integrate. So we're going to get the natural log of y equal to 9 times the natural log of x plus c. Is now a good moment to try and solve for c? Maybe, maybe not. So let's just see. Let's point out, if we plugged in our initial conditions here, we'd have natural log of 4 equal to 9 times natural log of 1 plus c, but that's 0. So you'd have c equal to natural log of 4. And while that's totally fine, then you have to carry that with you the whole way. So then when we solve for y and do e to the whatever, then we're going to have, so let's just do it this way and then we'll do it the other way. So this is natural log of 4. So we're going to say that e to the natural log of y equals e to the 9 natural log of x plus natural log of 4. You write this as y equal to e to the 9 natural log of x times e to the natural log of 4. And then e to the 9 natural log of x is e to the natural log of x to the 9th, which is just x to the 9th. And e to the natural log of 4 is just 4. So you should get y equal to 4x to the 9th. I would not do it exactly. That's not my preferred way of doing it. Here's what I would rather have done. I would rather have waited on finding c and said, let's just go ahead and solve for y first. So if natural log of y equals 9 natural log of x plus c, then we write both sides as e to the stuff. So the left-hand side is y, the right-hand side is e to the 9 natural log of x times e to the c. I'm going to call that a as I want to do. Right, this is y equal to a times e to the 9 natural log of x is x to the 9th. And I think it's much better to solve for it here. Because then if we plug in 4 for y and 1 for x, you get a equal to 4. So then we rewrite this as y equal to 4x to the 9th. That seems easier to me than the way I did it over there. But really, whatever you like. As long as you're careful and once you have found a value for your constant, then everything you do to both sides, you actually do to both sides instead of just replacing like a constant with a new constant, then it's fine. But I would wait until here. Questions about any of that? Oh yeah, let's do that one. That was pretty close. Okay. Yeah, we'll do this one, then we'll do some more first order linear. And we'll see what else there is to see. Let's say we wanted to solve this terrible differential equation. We're going to solve, I think it's 2. I try to number things sometimes. Solve dl dt equal to k times L squared times natural log of t, given that L of 1 is equal to negative 1. Okay, so here's a question. Is this equation pure time, autonomous, or non-autonomous? Well, let's ask them. So first of all, is it pure time? Yes or no? Yes, no. Definitely not, because there's an L right there. Is it, and for the same sort of reason, it's not autonomous because we have a T right there. So it's definitely a non-autonomous differential equation. It is separable. We can easily bring all of our dependent variable L to one side and all of our independent variable T to the other side. Also, that K there might be misleading, but that K is just a constant. So if you see a letter that isn't one of the ones that's in your DL DT or your D whatever, you should assume that letter is just some constant that they decided not to specify. All right, let's solve it. Okay. So I'm going to divide both sides by net L squared and get 1 over L squared DL equal to K times natural log of T times DT. Fun times. So the integral of the natural log of T. How many of you have memorized the integral of natural log of T or natural log of X? I'm not saying I expect you to have. I'm just really curious. Okay. It might be worth memorizing. It comes up maybe just often enough that you're like, oh, I have to do this thing again. But here's how we do it. So the integral of the natural log of T, dt, is an integration by parts problem. We're going to let u equal the natural log of T. dv has to be the rest, which is dt. Our du is 1 over T dt. Our v is 1 times T. I will point out, because I see this mistake so frequently, the integral of natural log of T is not 1 over T. The derivative of the natural log of T is 1 over T. The antiderivative of the natural log of T we're about to find. Let's see, it's going to end up equaling u times v, so T times natural log of T, minus the integral of v times du, so T times 1 over T dt. That's going to be T times natural log of T minus the integral of 1 is just T. I'll see if you like. So it might be worth it for you to memorize the fact that the integral of the natural log of X is X times natural log of X minus X. Or sometimes people write it factoring out the T as T times natural log of T minus 1. But I don't usually write it that way. Cool. So we end up getting that. Did I hear someone talking on Canvas, or am I just hearing things? No, I don't think so. Okay. So on the right-hand side, we're going to have T natural log of T. Oh, K times T natural log of T plus T, or minus T. Good Lord. There. Okay, we're going to squeeze in the minus sign there and turn my plus sign into a T. That's terrible. And then I'm going to write plus C, but I don't need the plus C to be in the brackets because a constant times a constant is just going to be another constant. So you all can see what I'm writing. It's K times bracket T natural log of T minus T plus a constant. On the left-hand side, I'm integrating L to the minus 2. I'm getting L to the minus 1 divided by minus 1. All right. So now I'm trying to solve for L. Couple things. I'm going to multiply both sides by -1, and it's not actually really going to change the right-hand side. Here's what I mean. If I have L to the minus 1 equal to -1 times a constant, is this going to give me a new constant? I could call it something else if you wanted me to. I'm just going to call it K. So I'll have T natural log of T minus T. And then -1 times C is another constant. Let's call it C again. Kind of annoying, but totally fine. And then this L to the -1 is really 1 over L. So then I'm going to take the reciprocal of both sides. You could also think of this as multiplying both sides by L and then dividing both sides by everything here. But you could also just take the reciprocal of both sides and say that, sorry, I'm just way zoomed in still. Sorry, let me back out just a little bit here. That L is equal to 1 over K times T natural log of T minus T plus C. Now I might have missed I won't say I missed it, but I might have gone further than I wanted to have found my C value. It might be good to find C here, but I think it's probably better to try and find C at this step here where C is kind of almost already isolated. Question? Mm-hmm. Yeah, it would. But then I'm multiplying, but I want to solve for L. So from this step to this step, this would have been minus, like this right here is minus L to the minus one. But then from this step to this step, I'm multiplying both sides by -1. I know it looks like I didn't do anything to the right hand side, but what I really have here is that this is K1 and this is C1, and then this is K2, and K2 is equal to the negative K1, and this is C2, it's equal to the negative of C1. This is super annoying, but it's what people do. So I should show you the thing people do. And then finally, so at this juncture right here is where I'm going to try and solve for C. So if I plug in -1 for L and 1 for T, I get -1 is equal to K times 1 times 0 minus 1 plus C. So it looks like C is going to equal K minus 1. Yeah, interesting. Sure. So what I have here is that L is equal to 1 over K times T natural log of T minus T plus K minus 1. Interesting. I fell into my own trap here. Not my own trap. I made the mistake I've encouraged you all not to make. So I solve for C at this juncture here. No, I'm okay. That's fine. Sorry, I thought I fell into my own trap. So I should be plugging in C equal to K minus 1 right here. And then that has to travel with the whole thing. But that just means I'm plugging it in right here. So I'm totally safe. I didn't do anything not allowed. Okay, I'm good. I'm good to go. There's my L as a function of T. Kind of gross when you have to take the reciprocal of the entirety of one side, but it does happen. So that's what we have to do. There's nothing else. You can't take the reciprocal of like each part. It's the reciprocal of the whole thing. Cool. Not you, not you, not you, not you. There we go. Oh, and then there's that one too. Question for you all. So everyone is talking about first order linear differential equations, right? No one's like skipping it. I mean, even if they were, we'd still be doing it here. Um, has anyone gotten past that yet and started talking about what's the word, Euler's method? Not my favorite, but we'll do an example. But let's do a little more first order linear, and then we'll talk about Euler's method for a little bit. It's kind of cool, but it's super annoying to actually like do in practice. So where'd you go? Other examples? Yes. So let's say we wanted to solve the following. T squared y prime plus 3t squared y equals t cubed, which is definitely looking like a first order linear, except I have everything multiplied by, I have a t squared, but I don't want it. So here's what I want you all to do, and I do want you to do this. So first divide everything by t squared, and then find your integrating factor. So step 1, divide by t squared. Step 2, find your integrating factor, which you might be calling I of t or mu of t, whatever you're calling it. Do it. we should have so far. There are differential equation written in the standard format for a first order linear is y prime plus 3 times y equal to t. And then our integrating factor is e to the integral of the thing multiplying by a positive y. So e to the integral of 3 dt, which is just e to the 3t. Then, and again, I'm not exactly sure how much they want you to show. I like to show the work of multiplying everything by e to the 3t, saying I have e to the 3t times y prime plus 3e to the 3t times y equal to t times e to the 3t. And the whole point is that this whole left-hand side is just the derivative of e to the 3t times y. Which means we can then jump to saying that just e to the 3t times y is equal to the integral of t e to the 3t dt. And so then we integrate the right-hand side using whatever method is appropriate. In this case, it is integration by parts. So we're going to let u equal t, dv equals e to the 3t, du is 1 dt, and v is e to the 3t divided by 3. So the integral of that should be my u times my v. So t e to the 3t over 3 minus the integral of v du. E to the 3t over 3 dt. So on the right-hand side, we should get e to the 3t times y equal to, on the right, 1/3 t e to the 3t minus 1/9 e to the 3t plus c. Finally, and this is where people kind of go different directions. You could just write the whole thing divided by e to the 3t. I personally think it's better, although it's not really better, I just like it better, to divide each thing by e to the 3t and then simplify the terms. So if I was dividing each thing by e to the 3t, I would my final answer as y of t equal to 1/3 times t minus 1/9 plus c divided by e to the 3t. Plus, then if they had given us an initial condition, we would solve for c, but they didn't, so we won't. I should ask, has anyone talked about tank problems? Like where you're putting stuff into a tank and then you're draining the tank also? Okay, great. No one's talked about that? Cool. If anyone does talk about it, tell me because we can do some examples. It's really, they are also first order linear differential equation problems typically. It's just that the setup is kind of on you. You have to figure out how the setup works and then solve the differential equation. So it's a little bit more involved. It is kind of neat. There is really a really kind of cool fact about the tank problems, but we don't need to talk about it. I guess we shouldn't spend our time there. Let's do one more first order linear, and then we will talk about some Euler's method. It's not pronounced Euler, by the way. It is pronounced Euler. If anyone's pronouncing it Euler, they're wrong. It's the guy's name. It was pronounced Euler. Okay, so let's look at this next one here. Ty prime minus 4y equals t to the 6th e to the t squared. Oof, looking gnarly. Okay. So first we're gonna do first what should I do? Yeah, standard form always. And you could even argue first, maybe you could look and see it. No, I think standard form, even if you're thinking it might be separable. So standard form is going to be y prime minus 4 over t times y equal to t to the 5th e to the t squared. Yeah, cool. Okay. It is sometimes, no, I should not say that. Sometimes you can do these separately. Even when you can, it's usually actually easier to just to do them as first order linear. Because if it's a first order linear that's separable, the separable differential equation, the integration is usually actually kind of uglier. So I would recommend if it's first order linear, just do it that way, even if you could separate it. So let's find our integrating factor. So this one is one where, again, we don't want to get tricked. Our integrating factor is mu of t equal to e to the integral of negative 4 over t dt. If there's a minus sign there, it has to come along into the integral there. Because again, our standard format is y prime plus p of t times y equal to q of t. So there's a minus sign there. The minus sign gets sucked up by the p of t. That's going to equal e to the negative 4 times the natural log of t. And it is vital is maybe not the right word, but it is really in your best interest to simplify this as much as you can. This simplifies as t to the negative 4th. Especially, like if you had left this as e to the negative 4 natural log of t, multiplied the right-hand side by it, and then we're trying to integrate e to the negative 4 natural log of t times t to the 6 of e to the t squared. Kind of gross. Or sorry, t to the 5th e to the t squared. So it is definitely necessary, I think, to simplify your integrating factor. So we multiply everything by the integrating factor. So we're going to get, let's see. Again, and be careful because I was making this mistake kind of just now, is you're taking your equation written in the standard format and multiplying everything in that equation by t to the negative 4, not the one before it, which I was kind of accidentally doing. So I'm going to get y prime times t to the negative 4 minus, I am going to simplify this. 4 over t times t to the negative 4 is 4 times t to the negative 1 times t to the negative 4, which is 4 times t to the negative 5th. Times y equals t to the negative 4th times t to the 5th is just t times t squared, t to the t squared. The reason I think I should simplify this, although you shouldn't actually have to, because if you found the right integrating factor, it should always be the case that the left-hand side is just the derivative of the product. But I like being able to see it. I like being able to see that, oh yeah, of course, this is the derivative of y times t to the negative 4th. Look at it. You get y prime times t to the negative 4th, cool, plus y times the derivative of t to the negative 4th, which is negative 4 t to the negative 5th. Oh yeah, it's totally the right thing. I like seeing that the work I've done is correct. And it's still equal to that. And so then we anti-differentiate both sides and we get y, okay, I don't want to write times t to the negative 4th. Y divided by t to the 4th is equal to the integral of t e to the t squared dt. I thought I had an initial condition, but I guess not. Whatever. I feel like we should be able to integrate this without doing any kind of extra work here. Because I know that if I were to let u equal t squared, my du would equal 2t dt. So I can really think of this as essentially e to the t squared. Not quite. I need to fix it. I'm going to fix it by taking the derivative and seeing how much I'm off by. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of e to the t squared should be e to the t squared times 2t. I don't have a 2 there, so I need a 1/2 here. Or you could do the u sub, right? You could totally say u equals t squared, du is 2t dt, 1/2 du is equal to t dt. So that's going to be the integral of 1/2 du e to the u, and then you get 1/2 e to the u plus c, which is 1/2 e to the t squared. I just think you can get away without doing it, and that's totally fine. Finally, multiply everything by t to the 4th. So we get our solution that y as a function of t is 1/2 t to the 4th times e to the t squared plus c times t to the 4th. Once you've done enough of them, they start to feel very kind of rote, or like you're doing the same. Like it's kind of, I mean, it's a more complicated plug and chug, but you're really just kind of, you're doing the same 5 steps every time. All right, so that's kind of the whole story on things we are able to solve, or I should say, on differential equations we are able to solve or find the solution to. It's either separable or first order linear. And then you apply the appropriate process. Separable, again, is just separating and integrating both sides. First order linear, a little bit more work. Let's go ahead and talk about Euler's method. Do I have a graphy thing I want to show you? Not really. So, yeah, let's talk about this for a second. Do I love this example? Not really. So let's say we're going to examine the differential equation y prime equal to t plus y squared. And I'll point out, I don't think we can solve this one. Because first of all, it's not first order linear. What's making it not that? What's the problem? Is it the y prime, the t, or the y squared? It's the y squared, right? The y squared is making it not linear in your dependent variable. And it's not separable either. Right? There's nothing I can do if I rewrite this as dy dt equal to t plus y squared. There isn't any way I can get the y's on the left and the t's on the right. Because how could I bring the y's to the left? The only thing I can really do is subtract y squared. And then if you do that, and this, I just want to make sure everyone's clear on this. If you do this, you still have a t on the left, so we have to multiply both sides by dt. But if you multiply both sides by dt, then you've got garbage. The dy minus y squared dt. I feel bad even writing this down. No, it's not good. What I should have really said is that when you're trying to separate variables, the only things you're allowed to do are multiply and divide. What I should say, once you have dy dt on one side and everything else on the other side, the only things you're allowed to do are multiply and divide. So if you can't separate those things through multiplication or division, you're stuck. So this differential equation, as far as we're concerned, isn't solvable with the methods we have. So what we're going to do instead of solve it is we're going to try to estimate a solution at some various points. And this is where Euler's method comes into play. So what I'd really like to know is I want to estimate the value of y of 2. Which if I could solve it, I would just plug in 2 and then get a solution. But I can't. And I should be a little bit more specific. We're going to make some assumptions here. So estimate y of 2 given a couple things. Given that y of 0 is equal to 1, because just like any good differential equation, if you want to know some values, you have to have an initial condition. And yeah, and we're going to say that we'll talk about that. And we're going to be given a step size, and a step size, which we'll talk more about in a second, of 0.5. Okay. Let me talk about the idea of this before we do the calculations. The idea is the following. Let's pretend, although I don't really know. Oh, that's the thing. Oh, I hate doing this. Sorry, I just remember the thing I'm supposed to do here. So we're going to draw a direction field. It's my least favorite thing to do. So a direction field is essentially in the two-dimensional plane where you have t on the horizontal and y on the vertical axis. We're going to plug in values of t and y. Is this going to work? I'm like, is this going to work? Yes, it should work. Yeah, it's going to work. Bummer. Okay. So we're going to plug in values of t and y to get the slope at that particular coordinate. So for example, if you plugged in t equal to 0 and y equal to 0, you get a slope of 0. So right there at the origin, your tangent line is a little horizontal strip. Let me make some marks here. 1, 2, 3. We're going to try not to do too much here. So this is going to go by halves. Let's say those are all a half instead of 1. So that's a 0.5 and a 1 and a 1.5 and a 2, blah. As you might have noticed, I really don't like doing this. It's just because it's tedious, right? To draw all these little things, it's much better like to use something like, what's the thing called? I don't know. I'll find it. It's in. I have a graphical link. Basically, you can use a computer tool to like make the direction field, which is much easier than doing what I want to do. So let's say we plug in 0.5 for t and 0 for y. We're going to get the slope of 0.5. So basically, along this horizontal line, the slope is going to be the t value. So at 1, the slope is going to be 1. At 1.5, the slope is going to be 1.5. At 2, the slope is going to be 2. And then if we go up, let's go up to 1 because 1's easier. So now we're just going to add 1 to all those. So if t is 0 and y is 1, we're going to get a slope of 1. If t is 0.5 and y is 1, we're going to get a slope of 1.5. And again, I'm doing this as precisely as I'm able to. If t is 1 and y is 1, we're going to do the slope of 2. And then 2.5. And then, sorry, I know they start to look, once the slopes get too steep, they start to look the same. And then you could do more. You could do more. And then we're going to pretend like I did more. So here you'd have a slope of 2. Yeah, 2. Yeah, gross. No, slope of 4. Oh, 4 looks super steep and then even steeper. Yeah, okay. So we've got things like this, and they probably look similar, like that. Here's my pretend direction field. Okay. The point here is that you could then try to estimate a solution curve by, so if I start at y of 0 equals 1, so if I start right here, then I can say, well, great. If I start here, I should be going in that direction. And if I move over a little, I'm going to be a little bit steeper. So I'm going to kind of go up like that and then over more, right? It looks like I'm kind of doing that kind of deal. So that's kind of the idea of using a direction field to estimate a solution given an initial condition. If you take the point you're told to start at, t equals 0, y equals 1, and then you try to like draw the line that goes through that goes in the direction that has those kind of little direction field arrows as tangent lines. I know I'm describing it really well. Yeah. Okay. We're not actually going to do that. What we're really going to do is we're going to use Euler's method to say, okay, well, great. If I started here, what I'm going to do is and I'm going to draw this again, kind of. If I start here at the point 0, 1, I'm going to say, oh, great. Well, at that point there, the slope is 1. So I'm going to go my step size of a half in the direction that the tangent line is telling me to go. So I'm going to go in the direction of a slope of 1. So I'm going to go over a half and up a half. Like that. And then when I get there, I'm going to recalculate. I'm going to look there. I'm going to say, okay, great. Now what's the slope? To find the slope, I'm going to plug in this new point to my differential equation to find the new slope. And then whatever the new slope is, let's say it's like pointing that way, I'm going to go again over a half and up as much as I need to get to the new point. And it's just it's almost kind of like a recursive sequence where like you find your next value by finding the previous value and plugging in the new thing. It's a very similar idea. Is we're going to find each next point by finding the previous point. So what this breaks down to is you've got some formula I'm not in love with, but it's fine. So here's the formula for what we're doing. We're going to say that your next y value, y sub n plus 1, is equal to your previous y value plus, okay, here's the way I really like to think of it, plus the rise, right? If you look back over here, to get from this y value, let's call that y sub n, to this new y value, y sub n plus 1, I just need to figure out from there over there, if my slope is my rise over my run, then I need to figure out what the rise is. Okay, well, if the slope is the rise over the run, then the rise is the slope times the run. So in other words, what I need to have right here is whatever my slope is, aka whatever y prime is equal to at whatever point I'm at, multiplied by how far over I'm moving, which is called my step size. So the run, the amount we go over is always just going to be kind of given to us as whatever the step size is. And we're going to call that h for some reason. I don't know why we picked h, but somebody picked h. So it's going to be h. That's the step size, aka the run, multiplied by what we're going to write here is f of t sub n comma y sub n, where we take our f of t comma y is what your differential equation is equal to. In this case, t plus y squared. I don't know why they picked the notation they're using, but this is the notation. So there's your step size, aka your run, and there's your slope, aka your y prime. So the reason I'm saying all these words here is because when I first learned Euler's method, I was like, what the is going on? Like, it just seemed really bizarre that we were just throwing all these things in this formula. But really, the whole idea is you're starting at a point, and then you're asking, okay, I want to move over and up, and then over and up, and then over and up. And the over and up is determined fully by whatever the slope is at that point and how much over you're going. Okay, so now for the execution. So again, we're starting at y of 0 equals 1, or as I would say, a t value of 0 and a y value of 1. So this is my first iteration. Yeah. All right, so let's find the next one. If y of 0 equals 1, then my next y value, you can see all that. And I might call this y sub 0. So to find y sub 1, the next value, it's going to be my previous y value plus my step size, which we said was 0.5, times f of my previous y value and my previous t value. Sorry, that's a little ugly there. Writing this out more nicely, my previous y value was 1. My run is 0.5. And my slope, if I plug in my previous t and my previous y, this equation here is 0 plus 1 squared, which is 1. So not surprisingly from what we already talked about, this new y value is going to be 1.5. So graphically, what we've got so far, we started at 0, 1, and then keep making this too big. We went over 0.5 and went up to a new value of 0.5. So there's that first point is our T naught, Y naught. This next point here is our T1, Y1. And now we're going to do it again. So now to find the next TY coordinate, T is always increasing by the step size. So the next T coordinate should just be 1. The next Y coordinate is what we have to find. So our Y sub 2 is going to be Y sub 1 plus 0.5 times f of my T sub 1, Y sub 1. So that's going to be Y sub 1, which is 1.5, plus 0.5 times f of 0.5 comma 1.5. And this is where things start to get a little bit gross. So 0.5 plus 1.5 squared is 2.75. And then 1.5 plus 0.5, right? I think the numbers start to get gnarly pretty quickly here. This is going to be 2.875. Yes, I plugged in. So I'm doing, and I am kind of, I will avoid, I'm getting a little bit, I'm skipping my work a little bit. So that's my f of 0.5 comma 1.5. And then plugging that into the differential equation here. And I'm getting 0.5 plus 1.5 squared, which is 0.5 plus 2.25, which is 2.75. And then I'm multiplying that by a half and getting 1.375 and then adding 1.5 to get 2.875. As I often feel about methods like this, eventually you start needing a calculator to just do the calculations. Then you might as well just use the calculator to solve the thing in the first place or whatever. So then the next one here, we're going to go over half again and then up to 2.875. That's a 1 comma 2.875. We have to do this 2 more times till we get to an input of 2. Sorry, and I kind of abandoned my table over here. So what I'm using this table for really is these are the numbers that are going into my differential equation. So like for the next one here, I've kind of given myself not the best amount of room here. Sorry, I'm kind of writing all over the place. For y sub 3, it's going to be y sub 2 plus 0.5 times f of t sub 2 comma y sub 2. And here's my, n equals 0, n equals 1, n equals 2. So my y sub 3 is going to be y sub 2, which was 2.875 plus 0.5 times f of 1 comma 2.875. And then that's for things that I have to use a calculator, right? So my f of 1 comma 2.875 is going to be 1 plus 2.875 squared times a half plus 2.875 is going to be approximately 7.51. So then we're way up here, right? Like that. And then finally, one more time. So again, that's for n equals 3. My t is 1.5. My y value is about 7.51. If we do this one more time to find my y4, my t is going to be 2, and my y4 is going to be my y3 plus 0.5 times f of t3 comma y3, which is going to be approximately 7.51 plus 0.5 times f of 2, no, 1.7, 1.5, comma, 7.51. And then calculator it, we end up with approximately 36.44. So it gets pretty big here. I mean, but that the idea here is that if we actually knew the solution to this and plugged in 2, we might get something reasonably close to 36.44. Yeah. Yeah. So maybe the actual, so like, here's my kind of solution I made up, and maybe the actual solution looks more like this, where like we would actually be getting something maybe a little bit bigger. We don't know what the actual solution is because this is one we can't solve, but this is how we could do it. Yeah. I can't think of why it would be. Not that it couldn't be, but off the top of my head, I don't know the answer to that question. I don't think so, because it's usually unsafe to say something is always true. So my gut is that no, it's not. Especially if my slopes were negative, probably wouldn't be an underestimate. So probably not. Other questions about this, aside from why is it terrible? It's terrible. So as a reminder, this is what we're doing. You're taking your previous y value and you're finding the new y value by taking that old y value and adding the rise, which is just your run times your slope. So when you have this differential equation, it does have to be y prime isolated. And I would love to show you another one, but I don't think there's enough time to show you another one. So what can we do in 5 minutes? 5 minutes never feels like enough time to do anything great in this class, particularly. What can I say here that's worthwhile? Oh, I know what I can say. No, not really. Yeah. How about we just call it a day at 4 minutes to the hour? I think that's a perfectly fine choice. Office hours as usual over in